So let's continue with the proof of the convergence theorem, which stated that if f is a continuously differentiable function and alpha is a step size, then alpha should range between 0 to 2 by L, where L is the Lipschitz constant, and the minimum of this function should not be at minus infinity, it should be greater than minus infinity. Then this result will hold. That if you take the norm of the gradient of that function at xk as k tends to infinity, then the limiting value of that function should be equal to 0. So we were talking about the proof, and we had taken the help of descent lemma, where we substituted y equals to xk plus 1 and x equals to xk, and then we have this function. So this is an inequality. Now we can further simplify this to show that this is equal to f of xk plus the gradient of f at xk transpose. Now if you look at this thing, you can take the help of the convergence, the iteration, where you have your xk plus 1 should be equal to your previous iteration minus alpha times del of f at xk. So now you have this quantity over here, which is x. So from here you can use xk plus 1 minus xk is equal to alpha times the gradient of f at xk. So we will use this thing to solve our problem. So here we will simply write minus alpha del f of xk plus Lipschitz constant upon 2 times, again for this thing we will take the norm on both sides, and what we will get is, so since alpha is a constant, its norm will come out as alpha scat because it's a scat term here, and then you will have del f at xk scat. Okay, so this will be equal to f of xk minus, so from this thing we can take alpha as common, so it will be minus alpha times, so del transpose times del will be norm of f of xk scat plus L by 2 alpha scat times norm of f of xk scat. So you can write this as f of xk plus alpha can be taken as common, so you will have alpha L by 2 minus 1, and you can also take norm of f del of f of xk whole squared as common. Fine, so you can simplify this further to get alpha times alpha L by 2 minus 1 times the norm of del f of xk whole squared is less or equal to, because this sign will continue, so this is less or equal to f of, so if you multiply on both sides, so this was your f of xk plus 1, and if you multiply on both sides by minus 1, then you will get this thing, your inequality will get reversed. So this is alpha L by 2 minus 1 times the 2 norm of del of f of x k is less or equal to f of xk minus f of xk plus 1. Now what we are going to do is something which is very important, and it's a part of basic maths, that's called as telescopic summation. So we will see what does it mean. So for telescopic summation we will start, so our parameter here is k, so I'll start from k equals to 0 and write this equation again. So I'll have alpha times 1 minus alpha L by 2 times the norm of del of f at x0 squared is less or equal to f at x0 minus f at x1. So because when you put k equals to 0, your f of xk will be f of x0 and your f of xk plus 1 will be f of x1. Now continuing with k equals to 1, you will have alpha 1 minus alpha L by 2 here we will have 1 minus alpha L by 2. So this will be del f at x1 whole square is less or equal to f at x1 minus. Similarly, the summation will go on till k equals to our last iteration, which is n. So it will be alpha 1 minus alpha L by 2 norm of del f of x n whole square is less or equal to f of xn minus f of xn plus 1. Right? Now if I add all of these terms together, what I'll see is that some of the terms will cancel. So this term will cancel with this term, and this term will cancel with the next iteration's first term, and so on. So for the last iteration, my first entry will get subtracted with the second last element's last entry. So what I will be left with is, I'll have alpha 1 minus alpha L by 2. Because this is constant, it has no k, so there will be no summation on this term. And then when we add up all the equations from k equals to 0 to k equals to 1, I'll have a summation term where k will vary from 0 to n. Then it's norm del of f of x k, so k varies from 0 to n whole square, and this should be less or equal to, the only two terms here that will remain is f of x naught and f of x n plus 1. Now you have to use a term here, so you have to use something which has been given in the theorem itself, which is that the theorem states that your f minimum is less than minus infinity, right? Is greater than minus infinity. So what I'll say is, from here I'll say this is less or equal to f at x naught minus f min. So if this quantity is greater than this, then if I subtract something which is less than this, it will still be greater than this, right? So I can just replace f of xn plus 1 with f min, and this inequality will still hold. And we know that this quantity will be less than infinity. And we know that this is a finite quantity. Also, we know that this is positive. Why? Because alpha has been given in the range 0 to L by 2 by L. Okay. So what we can do is, we can write limit n goes to infinity alpha 1 minus alpha L by 2 times summation k goes from 0 to n norm of del f of xk ka whole square. This is less than infinity, which means that limit n goes to infinity, summation k varies from 0 to n, the norm of del f of xk whole square is less than infinity. And this thing can happen only if the norm of del f at xk goes to 0, right? So this limit will be valid only if this norm of del f at xk goes to 0. which means that we have proved our theorem that as k goes to infinity, this term should go to 0. The limiting value of this term at k equals to infinity should be 0. So hence we have proved our theorem. In the next video we will cover one more theorem.